In the previous lecture we were discussing about the tangential force balance. In this lecture we will focus on the normal force balance. We have already discussed about the normal force balance, but our objective of this lecture will be to write it in a dimensionless form. So, first let us write it in a dimensional form. So, normal force balance is pressure at the surface, pressure at the interface minus pressure outside minus the viscous normal stress this T is the only the viscous component of the stress tensor. So, again I am recalling the physical meanings of each of these terms. This is the pressure at the surface within the fluid, this is the outside pressure, this is the viscous normal stress, minus sign because pressure compressive is positive, stress tensile is positive, is equal to, this is the sigma into 1 by R1 plus 1 by R2, in the 2 dimensional only R1, that is R dash, and this is excess pressure or the disjoining pressure due to van der Waals forces of interaction if the film thickness becomes very less. Okay. So, we will try to write various terms. Major activity will be to write this term. So, we will write that first. So, T dash we have written in the previous lecture, but we will write it again. So, this should be dot producted with n. So, n is nxi plus nyj. So, this will be right. So, look at this now, let us write the expression for this. So, 2 mu this plus 2 mu okay. So, let us write the orders of various terms instead of going on simplifying this further, because we will have a explicit inference from here itself. So, this is of the order of UC by LC, this is of the order of UC by H naught, this is of the order of Vc by Lc, right. And then this is of the order of Vc by H naught. Look into the nx square, nx square is of the order of epsilon square. So, this here epsilon square will come, nx into ny, here epsilon will come, and ny square here 1 will come, but in Vc itself epsilon will come, because Vc will be of the order of epsilon into Uc. So, all Vc's let us write epsilon Uc. So, you can clearly see that irrespective of the dimension by which it is divided, you may make Lc as or epsilon over H naught by epsilon, right. So, this will be H naught, in the top there will be epsilon. Lc also the same thing. So, if we have converted all terms where they are comparable, Uc in the numerator, H naught in the denominator, you see that. So, this is of the order of epsilon cube, this is of the order of epsilon, again epsilon cube, and this is of the order of epsilon, right. So, we can argue that all terms are of the order of epsilon or less. Therefore, in the leading order viscous normal stress will not matter, because this term, this is a very important conclusion, that when you work out this term you will get this in the leading order either of the order of epsilon or of order which is even smaller than epsilon, and that makes this term in the leading order much negligible as compared to these two terms which are in the leading order of the order of 1. Therefore, very commonly you will see that in a fluid dynamic problem, when we write the interfacial force balance normal stress, many times people do not write the viscous normal stress at all. So, it may be a purposeful mistake, it may be a mistake without any purpose, just a mistake, but eventually that mistake will not matter, because in the leading order you will find that the viscous normal stress does not have a role to play so far as writing the boundary condition for thin film equations, and that is justified by this order of magnitude analysis of the viscous normal term. So, from now onwards we will not keep this in the analysis. Remember, this is very important. When you learn a subject, one is what is fundamentally correct. So, keeping this is fundamentally correct. Then for implementation with incorporating the necessary assumptions, this which turns out not to be dominating as compared to the others. So, that we have to keep in mind, not that this is 0. Okay. So, with this understanding, we can write. So, this term we will not write. The only thing that we need to calculate before proceeding further is 1 by r. So, from coordinate geometry 1 by r is nothing but this one, right. Yes, dot of course. Okay. So, 1 by r is the divergence of the unit normal vector, that is how it is, they are related from vector analysis with coordinate geometry. You will get this in elementary mathematics course. So, now let us write these corresponding expressions. So, this is I n is nx n. So, let us write minus epsilon del h del x I plus j, that is n. So, this n and s are so critical, that is why I have retained it in one part of the board, so that we can always have a look into it and do the simplification. So, this will be my del x prime of minus epsilon del h del x, and because this is a constant, it does not have a derivative with respect to y. So, del x prime is x into LC. So, 1 by minus epsilon by LC okay. So, we can write now various terms in the equation. So, if we want to write LC in terms of H naught, then LC is what, H naught by epsilon, right. So, this we can write minus epsilon square by H naught right. then what we will do is we will write this in corresponding non dimensional form. So, Ps this we can write right, where Pc is the characteristic pressure. We know Pc in terms of Uc, that we will use later on. So, this is P0 into Pc, sigma dash is equal to sigma into sigma 0, and this is Px into Pc. So, with that consideration, we will be able to write this in the following. So, Ps into Pc minus P0 into Pc. So, Ps minus P0 this is negligible, this red colored thing is equal to sigma 0 into epsilon square by H naught, we have divided by Pc with a minus sign, minus sign is there here. Here there is a minus sign, right, plus Px. So, normally Pex in a dimensional form, it is important to see that how we write it. So, there is I give you an example in which it can be written in terms of the film thickness. So, this A is called as Hamaker constant. So, this Hamaker constant gives you the strength of the van der Waals force, and you can clearly see that as the film thickness becomes smaller and smaller, this becomes very large and it can dominate over all other terms. So, this is a non dimensional representation of that. So, you can write Ps minus P0 is equal to minus sigma 0 epsilon square H naught Pc is mu Uc by epsilon square Lc, right, mu Uc by epsilon square Lc. Now, H naught by Lc is epsilon. So, one epsilon will cancel. H naught by Lc will be epsilon. So, that epsilon will cancel with 1 by epsilon. So, you will get Ps minus P0 is equal to minus, now mu Uc by sigma 0 is capillary number. So, minus epsilon cube by capillary number into sigma right. So, now we have got all the governing equations and boundary conditions in a non-dimensional form. So, we will write a summary of all the governing equations and boundary conditions in a non-dimensional form in one side of the board. So,
why did you retain terms of the order of epsilon cube over? In an early stage you have neglected terms of the order of epsilon and epsilon square.
see, it all depends on the capillary number. So, there is a capillary number dependence on the top of it. So, it all depends on, so although this epsilon cube is retained, it is linked with the capillary number. So, the strength of this term will be governed by the capillary number, right. So, this is not like of the order of 1, 100, 0, 0.1, we do not know what it is, right. It will come, so it is what? It is mu uc by sigma 0, right. You do not know what is uc, you do not know what is sigma 0, you do not know what is mu. So, this is a very important point, because we do not know what is capillary number, it is better that we retain this. If the capillary number itself is large, then this will not be important. But in other cases, the other multipliers are known to us, that they are of the order of 1 or whatever. So, when you have epsilon square, you are able to neglect that. Okay. So, I will erase all the terms now, and from your previous day notes I will write all the governing equations and boundary conditions in a non-dimensional form. Summary of governing equations and boundary conditions in dimensionless form. Okay. So, let me write that with the help of you, because you have already taken the notes of this. So, continuity will be just like the x momentum So, we considered the dimensional body force as f x prime along x. So, right, epsilon square L C square, just check once with your notes, right. I do not have the ones which I did in the previous class. So, just check with your notes.
It should be epsilon square L C square, because that should be h naught square.
Epsilon square L C square, okay.
Because the scale of the viscous term was mu u naught by h naught square.
So, if give an example to see whether it is dimensionless or not, just if we have confusion. So, f x you can write say rho g as of the order. So, example is Okay. So, okay, but epsilon or epsilon square will not come out of the dimensional analysis. So, okay, I mean if you have taken your notes, fine, I keep it epsilon square. Then y momentum, zero is equal to this will be epsilon cube LC square by mu UC. With a minus sign, right. So, this is the governing equation and boundary conditions. Kinematic boundary condition, V at the interface is equal to del H del T plus U del H del X, right. Okay. Then tangential force balance, so del U del Y is equal to epsilon by capillary number, right. And normal force balance, P s minus P 0 is equal to what is that, minus epsilon cube by capillary number, we have just done that, into sigma right. So, these equations are important because see, except for the derivative terms, we do not have to really care about the derivative terms because we have already constrained all these to be of the order of 1. So, except for the derivative terms, everything else will decide what is the characteristic velocity scale, what is the characteristic pressure scale and so on. So, how do we ascertain the characteristic velocity scales? By looking into the dimensionless governing equation and appealing to the physics of the problem, that we will take up in the next lecture. Thank you.